Implement the k-nearest neighbors algorithm in which, given a set of data points and a query point, use the labels of the k-nearest neighbors in the data to make a prediction for your query point. Okay, thanks for being back here today, Raj. It's really good to have you here. Can you quickly introduce yourself for our viewers?
Yeah, thanks so much for having me back. My name is Raj, and I'm currently a machine learning engineer at Snapchat, where I am primarily working on generative AI initiatives for Snapchat.
Okay, awesome. Yeah, so you have a really cool background then. So let's get right into the question. Implement the k-nearest neighbors algorithm in which, given a set of data points and a query point, use the labels of the k-nearest neighbors in the data to make a prediction for your query point.
So, my understanding is that k nearest neighbors requires us to use some sort of distance metric in order for us to determine what closeness is. Can I assume that we can use the Euclidean distance for this?
Yeah, I think that's a great place to start.
Gotcha. Um, and so can I just assume that uh, like I have some sort of training data set and like the input features, let's say we can call it X, is some sort of NumPy array with like an arbitrary number of features. So maybe that would be like a matrix with dimensions n by d, where n is the number of examples and d is the number of features.
I think that's a good place to start.
Okay. Okay. Sounds good. So that's all the questions I have for now. I think I understand what I need to do here. So before I start coding, I just want to map out the approach. So kind of as you mentioned, k nearest neighbors is when you predict an incoming data point based on the label of the nearest neighbors within the training data set. And we discussed that this was a binary classification problem. So I
Mhm.
think that, and we also discussed that, we would use the Euclidean distance. So I think that basically we can kind of have like two main functions here. Basically, one, which is going to calculate the Euclidean distance between 2 points. And then maybe I can just say like functions to define. Um, and then the second one can actually do kind of like the k nearest neighbors inference. There's no formal training step for the k nearest neighbors algorithm. Everything kind of happens at the inference step. And so this inference can
Mhm.
kind of do the main logic of calculating the Euclidean distance between an incoming data point and all of the training data points, and then kind of getting the labels of, the top K, or rather the closest K data points. Does that kind of make sense as far as my approach there?
Yeah, that makes sense.
Okay. Okay, cool. So I will go ahead and start coding that up if that's okay.
Yeah, go ahead.
Cool. So like we discussed, I'm gonna have kind of that Euclidean distance function, and that will take in two data points, and we can assume that these are both vectors, right? And those are going to be NumPy arrays. And then obviously I will make sure that I import NumPy. And then that is going to return a float. And I'll just kind of focus on, or rather, I'll just get like the skeleton here before I actually write the implementation. So that's going to be our first function, which is the Euclidean distance. And then I will define kind of like the inference function. We'll just call it KNN. And I'm going to assume that I have uh, that NumPy array that we talked about earlier that was going to be of dimension n by d. So that's also going to be a NumPy array. We also will assume that we have a ground truth data set that corresponds with that training data. So I can kind of clarify again there. Can I assume that I also have some sort of ground truth labels? And can we assume that the number of data points within the ground truth labels matches up with the number of data points in like the X input features in this case?
Yeah, so X train and Y train should have the same length essentially.
Got it. Makes sense. Cool. And then we will also take in K, which is going to be the obviously like the number of neighbors that we're taking or the number of neighbors that we're actually considering, and that will be an integer. And then we are basically going to be returning, I guess, in this case, it could be an integer or a float, but it's basically going to represent the ground truth label, or rather the predicted label of the inference. Yeah, so I think that makes sense. I think the other thing that I want to also pass in is the incoming data point, which I'll call x new. Yeah, and that's going to basically be the signature for the KNN inference function. How does that kind of all sound as far as the skeleton here?
Yeah, that looks good to me so far.
Okay, gotcha. Oops. Okay, so I'm gonna start implementing KNN, and I'll define the Euclidean distance afterwards. So first we need uh, kind of like the distances, right? I'm going to define that as an empty list at first, and I'm essentially going to iteratively calculate these distances and put them as a list. Or rather, yeah, we're going to have them all in the list form, and then afterwards we can basically take the smallest distances. So in this case, I will loop through the training data set, and we'll call each row xi, and then we'll say that the distance is equal to the Euclidean distance. We're just basically going to be calling this function above here, and in this case, we want to, or excuse me, this should actually be x new, and then we will append the distance here. So now we have all of the distances between the incoming data point and the training data points in a list. And so now we can actually kind of use a neat function within NumPy to get the indices based on the sorted order. So there's actually a function called np.argsort, which I'm going to utilize here. So I'll just call this top k indices, and we'll call this function And so by default, this will actually do it in descending order rather than ascending order. So I'm actually going to reverse it as well, which can be done by slicing it this way in Python. And then we want to make sure that we are only taking kind of the top K, right? So this is basically just a kind of neat way of getting the data points that are closest as by the Euclidean distance. So now we have the indices of the top K. And so we kind of talked about like the ground truth labels as being binary classification. So typically the way that K-nearest neighbors will implement this is it'll basically take a majority vote. And then we can kind of assume that, like in this case, K is odd, so a majority vote works out. So I'm going to basically call that top K labels, and we'll make that a list comprehension where we are, and this should actually be Y train, and we'll say this is dot item, which I believe you have to call because it's a NumPy array, just so you're getting the actual uh, number rather than just a kind of like sparse vector in NumPy. And then obviously we want to do it for these top k indices. Cool. So basically here we just have like some sort of list that will represent the labels of the k nearest neighbors. So now we kind of talked about actually returning the majority vote. So an easy way of doing this is kind of just taking the sum of everything in here because they're either going to be zeros or ones. So if the sum is greater than half of this, basically that means that the majority must have been the one label, or else it would be a zero. And this should be all that's necessary for the KNN inference. How does that look to you so far?
Yeah, looks pretty good to me so far. I'd love to see you implement the Euclidean distance function now.
Sounds good. Sounds good. Yeah. So, just like at a high level, the Euclidean distance is basically going to take the squared distances between each of the data points or like the corresponding data points within the two vectors, sum all of those up, and then take the square root of all of them. So a convenient way of actually taking the square, or rather squaring, the difference of each respective one in the vector is kind of by like taking the dot product of the subtraction of the entirely two vectors within NumPy. So we can kind of do something like this, where we subtract the two data points from each other, and this will be a vectorized operation. And then we can kind of do a dot, which is basically multiplying them together on each respective column, let's say, of this vector. And you have to take the transpose because, of course, they can't be the exact same dimension. You need to kind of have them. You have to rather have the columns of the first one match up with the rows of the second one in order to do a valid dot product. And then, of course, the dot product will take the sum of all of them as well, in addition to multiplying them. So this is just a convenient way of doing Euclidean distance in NumPy. And then, of course, you want to take the square root of all of them. Yeah, that's a convenient way of implementing Euclidean distance.
Okay, sounds good. Is there anything else in your implementation that you wanted to cover?
That should be it as far as the basic logic behind the algorithm.
Okay, great. I'm curious then, do you think you might be able to quickly test your code?
Yeah, we can test our code. So basically, we want to um, kind of create like our own training set here. So maybe we want to choose some sort of training data and labels such that we know the distances are going to be closer for some than others. So maybe I can pick something like, and I can choose like a new cell here. Oops, I think I did forget some syntax there. I should have put a comma there. Cool. So we'll call this maybe xtrain. And we'll just make them two-dimensional data points for simplicity, although this implementation should work for everything, or rather data points of arbitrary dimension. So maybe I can do something like this. where we know kind of like what these data points represent. And then this will represent the input features, and then we can define the labels for these, right? So that basically means that this data point will correspond to this label, this data point will correspond to this label, etc. So maybe we can choose like a first test case, right? Where we know that, okay, if we pick something like x new equals 0, 0, we know that the k nearest neighbors in this case are going to be these 3 data points because 0, 0 is closest to these 3. And then we know that the majority vote amongst these 3 will have us return 0. So we know that this should return, and rather, of course, we have to also define k here. This should return 0. It might return the float version of it, or will return the float version of it, because we're going to be taking the sum here. I'm actually not entirely sure to return an integer, but maybe we can change that once we get the result there. So let's try calling this. Maybe we can do print KNN xtrain. I did just notice that we did not actually define these as NumPy arrays just yet, so I can maybe put these as NumPy arrays directly. Okay, so we have xtrain, ytrain, and we're passing in new, and this is going to be k. What did I do here? I think that Euclidean distance. So it's saying that the 2 values x and y are lists. So maybe we can go ahead.
You might need to run cell 3 again.
Yeah, I think that makes sense. So this is returning 1 here. So in this particular case, I was expecting 0 because I thought that these 3 would be closer, but let me just kind of verify that here, right? So maybe I can actually see by setting a breakpoint here, kind of like what the distances are, and then make sure that this is actually getting. Maybe I can put like a breakpoint here as well, and make sure that I run this again. So this allowed us to set a breakpoint, and let's actually check what distances was. Okay, so that was expected, right? Because we knew that we needed to get the top 3 distances here. So something else must be going on, but it seems like at that point we're okay. So maybe we can say continue, and let's just check kind of what the top k labels looks like, right? Um, top K labels that should be defined. Oh, I think that's something. Let's try that again. Ooh, I'm not sure why that's happening. The drag point should have gone away. Maybe.
I think your current breakpoint is before top K labels, right?
Yes, exactly. Thank you for pointing that out. It should be after here. Okay, so now we should be able to see what this is. And let's see what top K labels is here. So in this case, we got 1, 1, 0. So that means that, so let's check what top K indices was. So this was 3, 4, 2. So I'm wondering if I made the incorrect assumption that the argsort actually did it in ascending order. So maybe that I need to change that. So let's try one more time. So let's say what? Okay, yeah. So that was the incorrect part, which was that this function actually was defined the other way than I thought it would be. So now we've basically debugged that, and so we got the correct expected case.
Okay,
Okay,
perfect.
so maybe we should try one more, just to make sure that that wasn't just a fluke. How does that sound?
Yeah, that sounds like a good idea.
Cool. So maybe we should try, let's say, test case 2, and we'll say x new equals 2, 2, and we can also do k equals 3 in this case. And I think that it's fair to assume that, the expected result would be 1 in this case, because the closest ones should be the next 3. So let's just verify that. So we'll just say the expected is 1. Oop, we did not take out our breakpoint, and that was 1. Got it. So we verified with those 2 results.
Okay, perfect. All right, I think this is a great place to pause and go into some follow-up questions. So I'm curious about whether or not you would change your code at all if, let's say you wanted your code to be able to handle like multiple different types of distance functions. How would you change it?
Yeah, so maybe you could basically also pass in distance as a parameter to the KNN function, and that could basically represent your distance function. And then basically, you could pass in that case, like the Euclidean distance, or any distance function, assuming that you kind of had like 2 parameters that represents like the 2 data points.
Okay, so the user would pass in a function themselves.
Yeah, that would be one way of kind of like abstracting away what the actual kind of like logic is, because in this case we're explicitly calling Euclidean distance. But again, we could have that as a
Yeah.
parameter called distance.
Okay, yeah. What about if you wanted to support like a finite, like fixed set of different distance metrics?
Um, yeah, so maybe then you could use like a dictionary to represent
Mhm.
all of those distance functions. So maybe you could have like each key that corresponded to that function of how you computed it, and then you could pass in the kind of like string to the parameter of KNN, and that could
Mhm.
correspond to the
Yeah.
key within the dictionary. And so then basically, that would, and then like in the logic of your KNN, you could basically just call this like global dictionary to actually get the function.
Okay, great. Yeah. And one last question is, if you were to add any sort of like error handling to your KNN function, what would you add?
Yeah, that's a good question. I think that one thing that could go wrong is that perhaps the dimensions of certain things didn't match up. So, for example, if
Mhm.
the dimension of like xi in this case doesn't match up with x new, um, for whatever reason, right? Like either the dimensions of the entire X train array is entirely different than X new. Um, you could basically flag that, right? And you can basically, I guess, get the shape of both of those arrays and then say that, hey, check, assert. You could do an assert statement in Python and say that those have to be the same dimension.
Wait, so you're saying you want X train and X new to be exactly the same shape?
Not X train, XI in this case. Or another way of doing it is you could also compare the second dimension of X train and X new, right? Because you want to make sure that they have
Mhm.
the same number of columns. So that's another way of doing it, and,
Yeah,
and you can kind of like index the second one.
yeah, that makes
And
sense.
again, like yeah, and
Yeah.
I think NumPy has a shape attribute that basically represents the dimensions.
Mhm. Yeah, yeah. So you probably also want to check the fifth dimension of X train and Y train match, and also that Y train indeed includes only zeros and ones as you expect, right?
Yep, yep. Those are both things that could be checked as well. I think that's totally valid.
Yeah, and what happens if the length of X train is actually less than K?
Right, right. Um, so in that particular case, you could basically, you could basically just check it, and then like where we're doing this logic, uh, where we're checking if the sum of top k labels is greater than k over 2, you could just do the max
Hmm.
of k and the length of x train, right? Because in this case, let's say k was 3 and you had two data points, you just want to be kind of comparing the majority within there, right? It's almost like not, I guess, valid to have k greater than the length of x train. Um, so, I mean, you could also kind of handle it by saying that, hey, it has to be, you know, uh, kind of greater than or less than or equal to the length of X train.
All right, yeah, so you probably want to return an error in that case, right? Because otherwise you would give an incorrect result.
Yeah, that makes sense. That makes
Yeah,
sense.
yeah. Either that, or I imagine you can adapt your code so that it still works, and it just takes like what nearest examples they can find, even if it's less than K, and returns a majority vote from those examples, right? Even if it's not K examples.
Exactly, exactly. It just totally depends on how you want to consider like valid input, right? I think that's totally up to maybe the person who's implementing the function or like the user of a library that you could be creating for this. So I think either or is a valid option.
Okay, cool. So I think that's a great place for us to pause on that then. I'd love to hear from you how you think this interview went. What do you think went well, and what do you think you would have done differently?
Yeah. I think that what went well is that we settled on the logic of the implementation pretty easily. And I think that we were aligned kind of on like how to implement the algorithm. We were able to align on using binary classification. We were able to align on using the Euclidean distance. And we were kind of able to implement both of those in a fairly simple way. So I think that's great. I think that there was a little bit of rockiness when it came to my own assumption that a certain function worked in a way that I thought it worked. I basically assumed that it was going in it was actually that I assumed that it was going in descending order, but really it was going in ascending order. That's the default way, and that's how to get the closest neighbors. So we could have saved ourselves a little bit of debugging time by not doing that or making sure we verified that assumption before we were using a built-in function. I am noticing that this is returning a float. Actually, it seems like it's actually returning an integer. So I think the typing is just a little bit off there. Yeah, so there's just a couple things that it could have gone a little bit better.
Okay, cool. Yeah, I actually really liked how well structured your code was, that you outlined all of your thinking first, including like all of the functions you wanted to implement before going into the actual implementation. So that definitely made it really easy to follow, and your code is really easy to read. And I definitely love that. And yeah, like you already mentioned this, like um, it would have been good to check that you understand exactly what like numpy.argsort does, for example. However, you did a really good job of debugging it once you realized that it wasn't working the way you expected it to. So I liked that you're really effective with using your breakpoints and using the debugger, which I haven't actually used Colab's debugger before, so it was cool to see it in action. Um, yeah, and then I would have loved to see some more error handling in this code, and also possibly one design choice that you could have made. You don't have to, but if you wanted to do different types of distance functions, you could put the KNN function as a class instead, and then just have like helper functions for the different distance functions and so on. But yeah, overall, like I thought this was a really fantastic interview. It was really well structured, well thought out, and ultimately you landed on a correct solution. So thank you so much for being here, Raj. And thank you everybody for watching. Good luck if you have any upcoming interviews. Bye, everyone.